Okay, so I'm making this video on phase diagrams just for some extra practice. So here's a phase diagram, and people kind of get a little bit scared of them, but they're really just like any other graph. So on the x-axis, we have temperature, and it's increasing left to right. And on the y-axis, we have pressure, and it's increasing as we go up. And I want to do number 36. And it says, which letter represents A, the gas phase? So the gas phase is always going to be here where Y is. So let me write gas. Then liquid, it's going to be up here in X. And solid is going to be here at W for any phase diagram. But it's easy to confuse these if you memorize them. So here are two tricks for remembering. One thing you have to remember is between the three states of matter, gas, liquid, and solid, the most compressible is gas. So gas is highly compressible. And for this reason, we'll always find gas in the lowest pressure region, which is why gas is going to be underneath this line. So that's how you can always remember where gas is, because as pressure goes up, the molecules of a gas go closer together and they can either liquefy or solidify. So they're just becoming more, the state of matter is becoming more dense. Okay, and then the second way to remember, so in this scenario, you have to think about pressure. And then in the other scenario, you can just think about temperature. Well, we know that if you want to get a solid to melt, you just raise the temperature to make it a liquid. So that's what's happening here. That's why solid is first and liquid is second, because as you go higher in temperature, stuff melts, like ice, for example. Cool, so that's how that works. And D is the triple point, and this is the state where all three states of matter exist. And it's hard to come up with an example. Personally, I never have seen this, but it does exist. The best example I have is dry ice. So during dry ice, that's carbon dioxide ice. As it's in its solid form, you can also watch its vapor form. It vaporizes on the spot at certain temperatures and pressures, of course, because that's the whole point of a phase diagram. It's supposed to show how something acts at a certain pressure or temperature. Okay, so let's answer some questions now. This says, what is the normal boiling point? So normal just means standard conditions. So the conditions we're in every single day when we wake up, we're at sea level. So that's 1 atm pressure. That's the pressure we're normally at. If you go higher, it's less, because our atmosphere is going to have less gas particles in it and therefore become less dense. And then if you go lower, it's actually a little bit higher, which is why when people dive underwater, in addition to the weight of the water on them from the pressure and stuff, it's just higher pressure as you go lower. So it says, what is the normal boiling point? So all we have to do is find what's the boiling point for something at 1 atm. So that's pretty easy. Well, boiling is when water turns into vapor, right? So let's look at where it's a liquid and where it's a gas. This line represents where it shifts from between that. So all we have to do is go from one and like put our finger and try, my line's not that straight, but try to draw a straight line. And this is where it changes from liquid to gas. So it's 40. So that's the normal boiling point. And then it says, what's the normal melting point? Well, let's erase that. Cool. So now we can do the normal melting point. Well, 1 atm is our normal pressure. But this time we're going from solid to liquid because we're melting. So we just draw a straight line and go down. That's about at about 12 degrees Celsius. If you're at 1 atm, you're going to melt, or not you, but whatever this is showing. So let's show another example. Here we were, let me rewrite some stuff. So this was our solid, this was our liquid. So at 1 atm, we noticed that boiling happens at 40. And just as an experiment to prove to you guys that phase diagrams work, I'm going to bring the pressure down. Let's say we're on Mount Everest. I don't know what the pressure is on Mount Everest. I just know it's lower than sea level. So let's say we're like 0.8 atm. Let's see what temperature we'll need to boil whatever we're boiling. And it's a little bit less. It's like 35 degrees Celsius. So this is why we can boil things easier at higher elevations. Phase diagrams are just showing you how, depending on pressure, well, I guess, or depending on the mix of temperature and pressure, what you have to use, I guess. Like if you're at a different pressure, you're going to need different temperatures and so on, in order to melt something or vaporize it. Cool. So let's do a few more. When a liquid originally at 20 degrees Celsius and 1 atm has pressure reduced, at what pressure will it vaporize? So let's find 20 degrees, cool, and 1 atm. All right, so in this state, it is a liquid indeed, as the question mentioned. And it says at what pressure will it vaporize? So it just wants to know, we're just keeping the temperature constant, but we want the pressure to get lower, so that we can still get vaporization. So here it's about 0.5. I know it's a little bit off, but let's just say 0.5, because that's what the answer key says. So yeah, so as you can see here, in some cases, if you can't change the temperature, you can change the pressure to boil something. And actually, this is what they do in a lot of chemistry labs, like the chemistry lab that I work in. We have something called a rota vaporizer. And it's a machine we use to basically isolate a compound that we want. So let's say we have X plus A, and they're mixed together. Maybe A is 20% and X is 80%. These are parts in a solution. And we only want A, we don't want X. And the way we can get the A is take advantage of boiling points. So what happens is A has a higher boiling point than X. X has a lower boiling point. So we say to ourselves, cool, that means we can just turn up the temperature to this guy's boiling point, get rid of him, but we'll still have A because A won't boil. But the thing is, like when you're working in a lab, you don't want to waste time. You have so many compounds. It's not just this, you have many projects going on. So you want it to happen faster. So in order to happen faster, in addition to doing the boiling, we use this rota vaporizer to lower the pressure. So here's a machine, and we'll have it at about room temp, or whatever the boiling temp for X is. Let's say in this case, it is room temperature. It boils at room temp, slightly above room temperature, because if it actually boiled at room temperature, we wouldn't have to do this. So a little higher than boiling, than room temperature. So this is going to be set at that temp, but since it takes time for this to get it to that temperature, in addition, this machine, it'll make sure that the pressure, which is normally the pressure we're at is 960 millimeters per mercury, I think that's what it's called, which is equal to 1 atm. It'll bring it down to like 60 mmHg in here. So as you can see here, just like how when the pressure reduced here, we could get boiling to happen at the same temperature. we take advantage of that in this situation. So that's a real life application. That's like a machine that people have created that reduces pressure. It's a vacuum, basically. Cool. So let's do another example. When a liquid originally at 20 degrees, sorry, I can't even read, 20 degrees and 1 atm has its pressure increased, at what pressure will it solidify? Cool. So 20 degrees is here, 1 atm is here, and it is indeed a liquid. And it says, what pressure will it solidify? So in this case, we're actually, what pressure will it solidify? Okay, we're still keeping temperature constant, but this case, we're gonna go up because this is the solid line and we wanna see when it turns into a solid at the same temperature, but a different pressure. And this is the case, it's gonna be here, 1.5 atm. Cool. So we were able to do both of those. Let's do two more examples. When a solid at 1 atm is warmed, does it melt or sublime? Well, if it's at 1 atm, let's draw a straight line to see what happens when it's warmed. So we look at the temperature axis. Cool, so it's gonna melt. That's what happens when the pressure is constant. Here's where it changes. And then for the next one, when a solid is at 0.3 atm and it's warm, does it melt or sublime? So here's the solid. Oh no, my cat. No, Newton. Okay, he was walking on the keyboard. So 0.3 atm, I thought the Zoom was gonna shut down. And it's warmed, what happens? So here's the solid and it's gonna go to the gas phase. So solid going to a gas directly, it is going to sublime. So that's all phase diagrams are. So if you can read this phase diagram, you can read any phase diagram because all phase diagrams follow this type of general pattern when it comes to the shape. The pressure and the temperatures are just going to be a little different because all materials are going to be a little bit different. The last thing I want to say is water's phase diagram. It's a little bit different. This is inclined this way for everything except water. Water will be inclined a little bit more this way. And the reason is if this is a solid on this side and this is a liquid on this side, when we have a negative negative slope like this instead of a positive slope, well, this positive slope shows here, what is it showing? It's showing as pressure goes up, there's gonna be more stuff in the solid phase, right? Because there's more, like, I like to think of it as if we drew a straight line here, this is the area we get, and this ends up in the solid phase. But if we look at it here, if this is the line for water that I'm drawing now, when we look at it here, if we drew a straight line, just like this is the same straight line I drew, when we look at the area, there's more stuff in the liquid phase when we go up in pressure. So this arrow is representing going up in the direction of pressure. And same here, this one's up in the direction of pressure. So hopefully this explanation is making sense so far. And this is because this just, well, the phase diagram proves the truth. We don't have all the answers, I guess, to why it is. Yeah, it's kind of complex, but basically ice is less dense than water. And this is why ice floats. Because you should wonder why ice floats, because it's a solid version of water. Shouldn't it be more dense? And according to like buoyancy and stuff like that, denser objects sink when they're denser than the water or the liquid that they displace. So that means that water is less dense than the water it displaces when it's in ice form. So the reason for this has to do with the way the molecules arrange themselves. It has to do with the characteristic of H bonding. It's not, if you want to know more about it, you can look it up. But that's why water is the only phase diagram which is going to have this type of relationship versus this type of relationship. So I like to think of it as the area. So in this case, as you go higher in pressure, you'll actually have this much more area as liquid versus in a normal phase diagram, which all the rest of our materials on Earth have. It actually it follows the traditional route of what you would think would happen. It gets more dense as pressure goes up. So that's the only difference. The liquid is going to act the same, and the gas is going to act the same, and the solid is going to act the same in every other context, except for this. So hopefully that helped. And I'll see you guys in another video.